Okay, here we go. So, I'm Roger Smith, I'm a fault-tolerant technology, and I'm going to talk about multi-domain architecture and ARINC 653. So what we're going to do is we're going to talk about ARINC 653 review a bit, which has already been done, and computer architecture. We're going to talk about malware, fault tolerance, and performance. And so ARINC 653 is the Aeronautical Radio Incorporated Specification number 653. They got a bunch of them, and it's basically how you specify a real-time operating system. Now, as we saw earlier, there's used to be a whole bunch of different computers within an airplane or anywhere, and they decided that they would do a server consolidation project and put these all in one place, and they called it the IMA, or the Integrated Modular Architecture. And so they decided, well, if we have it all in one spot, we're going to need an operating system, and so there's a bunch of them, and one of them is ARINC 653. It's just a specification. As part of the specification, there is the apex, and there's a piece of software that sits between the application and the kernel that only allows the application just enough to make it run. And then there is something called spatial and temporal partitions, and what that means is that each one of these legacy systems got its own address space, and it runs in a specific time frame. We saw that earlier. And in addition to that, it has a health monitor and a recovery piece of it. But it has some drawbacks, and one of them is that it has a lot of overhead associated with it. So to do all this stuff, it takes a lot of overhead. And then also, if you get an error within a partition, oftentimes the whole partition fails. You either have to restart it or you have to blackball it. And there are malware vulnerabilities to it. And to date, people have mitigated the malwares by using virtualized systems. However, Symantec did a study of 200,000 of their users and found that 20% of the malwares that they found with these users were running virtualized systems. So it does happen. It happens in airplanes too. And a couple of years ago, there was a guy by the name of Hugo Tesso who took his Android and hacked a flight control system at a Black Hat conference in Amsterdam. Now, FAA and ESA said it did not work on flight certified hardware, but then we have that he said it worked. Also, Michael Hippion was talking to an aircraft manufacturer in Europe who said that they have to go through and sweep out Android malware weekly from their cockpits because employees were charging their phones with the USB port in the cockpit. And then there was a famous hack of United Airlines. Chris Roberts hacked in flight, through the flight entertainment system, got a hold of the engine controls and increased the thrust and made this thing climb and yaw. And he did it what he did is he got into the wires of the flight entertainment system and then broke into the computer system. Some controversy about that. We're going to get that into a couple of slides. But really what the problem is with the architecture, with the hardware architecture. And everything is located in one spot. So anytime that I want to attack anything, I have to have three pieces of information. I have to know how, when, and where to attack. So if I want to attack, go to the OK Corral at a gunfight at the OK Corral. So if I go to the OK Corral at high noon with a knife, I will not make it. My mom is going to be really mad because I took a knife to a gunfight. So it's not going to work. But you know, I could take a Gatling gun to the OK Corral at 4 in the afternoon. It's not going to work either. And likewise, I could take a Gatling gun to 6th Avenue at high noon, it's still not going to work. So I'm going to have all three of those pieces of information. The problem is that all three of those pieces of information is located in one spot, and that is the CPU address space. So here is the hardware. Let's see, how do you work this thing?
Little arrow goes forward to that. Do you see the 2 arrows there?
Ah, thank you. So over here we have what I'm terming a single domain architecture, and that is like a regular old computer system. And the problem is that if a guy is sitting in the seat and the flight entertainment system is on partition 3 and the engine control system is on partition 1, if I break out of my sandbox and get control of the CPU, I got the whole thing because I can get at any piece of that operating system I want. Here's the kernel. Here's the apex. It's all part of the operating system. Over here we have a multi-domain architecture, and we have 2 separate address spaces. We have one for the applications, and we have another set for the kernel. Same kernel, same apex, same everything. It's just in 2 different address spaces. And there's no way that I could get out of this system. So over here you can say, well, why didn't they put the flight control system on a different computer system? Well, really what you're saying is, why didn't they put it in a different address space? And that's exactly what this does. It puts it in a different address space. Next, I want to talk about some comparison features about the CPU overhead. A couple slides ago, we were talking about one of the drawbacks of the 653 architecture was the overhead. It takes a lot of overhead to do this stuff. And so why not put all of the overhead in a separate address space? And that's exactly what the multi-domain architecture does. In fact, the multi-domain architecture is kind of acting like a container system. So does anybody ever work with containers around here? So, you know, containers, they have like one centralized system that is acting like a ARINC 653 that doles out all the information to the partitions. But it's a lot faster. So here is a slide, and I apologize for the slide. I ripped it off from a YouTube video. It doesn't make a lot of sense, but there's a company called Parallels that makes container-based systems, and they presented a presentation at LinuxCon in Europe that showed that containers were 7 times faster than hypervisors when switching applications. Here's one, a comparison done by IBM, and what they did is they took 15 partitions over a period of 5 minutes, and this includes startup and shutdown. And containers were 9 times faster in the user mode and over 100 times faster in the kernel mode. And it uses far less resources. So in general, it's just a lot more efficient. And the reason is that in this system, if I'm on partition 2 and I need something from the kernel, I got to stop what I'm doing, put everything on the stack, then go over to the kernel and ask the kernel to do stuff, and then come back and put everything on a stack. I get an interrupt coming in from the outside. I got to stop what I'm doing. And the CPU has to handle all that overhead. Over here, if I want to put something here, if I get something from the kernel, I just put it in a wait state. Go over here and just pick it up again. Boom, you're done. If I got something coming in from the outside from an interrupt, I can go to one of those partition spaces that we're talking about that wasn't the kernel, that one of the CPUs is not idling, and I'll just do it then. So it's far more efficient to do with a separate address space. So multi-domain architecture gets near bare metal performance on the compute nodes, has far better network operations, and uses less CPU time, saves you time and money and power. Lastly, I would like to talk about the failure of partitions. And so the multi-domain architecture, because it has two different separate address spaces, if you have one piece failing in one address space, you can just reschedule an available component. Also, it uses other things like combinatorial mathematics. So for example, if you're going through Byzantine architecture, it would, in single domain Byzantine failure, if you're going into single domain architecture, it takes you 4 different systems to discover one error. In multi-domain architecture, it takes you 3 systems, can discover 3 errors, and still remain fault tolerant in some situations after 3 errors occur. They have to be different errors, but you can still remain fault tolerant. And so you compare the systems in comparing the single domain systems and the multi-domain systems in the hardware, you can have a CPU failure in a multi-domain system and still recover your system. You can have any component failure. If you have another component that can take over, you can still do it. And it can do it at the component level. If you have a voting system, you have a problem with one of the voting systems in a single domain system, the whole system gets voted out. In a multi-domain system, you can discover what the problem is internally and perhaps compensate for it and still remain a 3-system voting system when you're done. Sensors, I don't know. If they only got a single sensor, it can't help you out. But also, in a single domain system, if you have a problem with virus problem with your hardware, the only way that I know how to do it is to go back to what they call a puff definition. A puff definition is a physically unclonable function, which means it's like your iris or your fingerprint is physically unclonable. And each electronic component in your system has certain physical characteristics that you can identify with it. So it helps you out with like a Stuxnet problem. In multi-domain architecture, you can not only have the physical definitions, but it can actually determine that the physical properties of it is changing on the fly, dynamically, while it's in operation, so you can catch those sorts of things. You can't really do that with single domain architecture. In software fault tolerance, it's quite a bit different, and I'll try to quote from the spec. It's something about if you have the state of partition can fail, but since it fails, you have lost the state of it, and therefore only stateless partitions can be recovered. Multi-domain system is an immutable system, which means that it always knows the state of the system. So you can have a software failure in that state, and it can recover from it because it always knows the state of the system. Not only that, but if you have a software problem, you can replay it up to the point of the failure. Even a virus attack, you can replay it up to the point of a virus attack. So in single domain system, when you get a failure like that, you get a partition level failure. Multi-domain you get a thread level failure. You get a stateless recovery. You get a stateful recovery, and you get forensics analysis. So what I was saying is you can recover. You can replay the error up to the point of failure. Single domain systems, you detect viruses. Multi-domain systems, you prevent them. So it meets all the ARINC 653 specifications. It has container performance. It has virtualized system versatility. You can run multiple operating systems in multi-domain architecture in native mode, and it prevents viruses. Thank you. Questions?
Questions? Nope. Okay, thank
All
you.
right, thank you.